Good evening, everyone. Can you hear me and see the slides?
Yes, sir.
Yes.
Yeah. Okay. Um, so about the final assessment, we'll push that discussion to the end so that we'll have participation from everyone. Okay. So let's begin today's lecture. Like today's topic is biochemical processes for biomass conversion. So what are the biochemical processes? Can someone tell me? We've already discussed this.
So one is biomethanation.
Yes. The next
And
one.
next one, just a minute, sir.
Hmm.
Biomethanation and fermentation.
Yes. So biomethanation produces methane or biogas,
Methane.
and
Yes.
fermentation produces
Ethanol.
ethanol. Okay.
Yes.
So
Yes.
in general, we call everything as fermentation, but then, yeah, I mean, we distinguish it in this way. Okay. So fermentation is more of a local term for biochemical process, right? So, yeah. So the contents for
Sir, even
today first.
biomethanation is also a fermentation process only.
So, I mean, one part of it is called fermentation. I mean, it's fermented to produce some acids, and then there are methanogenic bacteria that form methane. So I'll explain
Okay.
everything. Although
Yes, sir.
it's, I mean, it's not technically right to call it fermentation because fermentation is normally when you produce ethanol. Okay,
Yes. Yes. Yes.
but in general, if you see all these probiotics, if you have you have curd, right? So
Yes.
curd is also said to be fermented, but you don't have any ethanol there, right?
Yeah.
So we call curd also fermented food, like it's a probiotic. Okay.
Yes.
So I mean that's the local colloquial language, I would say, but there are different processes in biochemical conversion. So we'll look at two of those processes in this one. So yeah, the contents for today. First, we'll look at the biomass conversion pathways that we had a short introduction to yesterday. Then we'll go on to biodigestion, the phases of biomethanation, the factors affecting the production of biogas, and we'll see the classification of biogas plants, a single stage and dual stage biogas plants, and then some commercial plants that are installed in India and other countries. Then what are the design considerations for the biogas plants? And then we'll go on to again, in the previous lecture, we have seen agricultural residues and biofuels, the classification, the primary, secondary, 1G, 2G, all of those things. Then we'll go on to the crop yield, what is crop yield and crop to residue ratio. And then the fermentation process, that is 2G ethanol and what process it entails, right? And the process is involved with 2G ethanol production, like the pretreatment and hydrolysis. And then we'll see a difference between 1G and 2G ethanol. I have a document here. I don't know if I can share that with you, but yeah, I think I'll share it on the chat when I come to that particular slide. Okay. Then the land footprint for producing 2G ethanol from various feedstocks. Okay. And then we'll go on to the discussion and Q&A. So it's going to be a long session, right? So it's heavy on material today. So biomass conversion pathways. So there are two types of conversion, as we have seen yesterday. One is biochemical conversion, and the second is thermochemical conversion. So in biochemical conversion, you have anaerobic digestion, fermentation. So anaerobic digestion produces biogas, fermentation produces ethanol. In thermochemical conversion, you have pyrolysis, gasification, and combustion. Pyrolysis produces bio-oils and biochars, okay, depending on how fast the pyrolysis is, the rate of pyrolysis. And pyrolysis is heating the biomass in the absence of air. Okay, you're subjecting it to very high temperatures. Then the second thing is gasification, where you subject the biomass to high temperatures, but with the limited supply of air, a limited supply of oxygen. So what happens is that it doesn't combust completely to produce so much heat, but then it turns into a combustible gas, like it's called syngas or producer gas, depending on what medium you're using, either air or oxygen plus steam. And using gasification, you can either produce electricity or you can produce syngas or producer gas, which can further be converted into various products, downstream products like hydrogen, methanol, ethanol, and biopetrol, biodiesel, and so on. Okay. Uh, Combustion is basically just for it's just to produce heat, and that heat can be used to produce electricity. Okay, so these are the conversion processes that are currently available and commercially available as on date. So what is biodigestion? So biodigestion is the decomposition of organic matter through microorganisms. So there are two types of biodigestion. So one is aerobic and the second is anaerobic. So we've discussed about this. So what is the difference? What is the difference between aerobic and anaerobic digestion?
So the
Yeah.
main difference is the presence
Mm-hmm.
and absence of oxygen and the product given out. So
Mm.
in anaerobic digestion, ethanol is the product, and
Mm.
in aerobic, it's carbon dioxide
Mm-hmm.
part.
Yeah.
Is it carbon dioxide partly?
Yes. Yes. Carbon dioxide, and you produce compost
Yes.
as the
Yes.
main product, right? And
Yes.
then in anaerobic digestion,
We get ethanol.
no, you don't get ethanol in anaerobic
No, no,
digestion.
no, no. We get methane. Methane. Sorry.
Yeah, methane and carbon dioxide. So yeah.
Yes.
So
Yes.
the gas produced in aerobic digestion is just carbon dioxide because it's just the bacteria is just respiration is happening, right? So the organic matter contains carbon, and then it's using the oxygen in the air to produce carbon dioxide. That's it. Okay. So that gas cannot be used, but then you can use whatever is left behind, the digested material that is rich in nutrients that you can use for the soil. Okay. In anaerobic digestion, you don't have much sludge or slurry left, but that has a lot of inorganics, the sludge, the digested sludge that is. But then the gas is combustible because it contains methane. Okay.
So
So
whatever slurry is left, you said, right, in anaerobic digestion,
yeah,
uh, then that can again be used as fertilizers.
you can, but then you need to ensure that
It won't provide much
yeah,
nutrient anyways, is it?
it won't provide much nutrients, and then you also have to ensure that it doesn't affect the soil quality because sometimes it may contain toxic materials also.
Yes.
That is toxic to the the organisms in the soil. And the
Uh,
reason is it
oh,
is all digested slurry, right? Which is already decomposed.
yes.
So you need to ensure that it is not harmful to the soil. But in general, it contains a lot of inorganics like nitrogen and also that's good for the soil in general. But yeah, you need to make sure that that is the case.
Okay, sir.
Okay.
Yes.
And yeah, so that is basically the difference between these two, aerobic and anaerobic digestion. So anaerobic digestion occurs in three phases. One is hydrolysis, the second is acid formation, Third is methanogenesis. Sometimes this acid formation is split into two parts. One is acidogenesis and the other is acetogenesis, where some acetates are formed. Okay. So I'll explain all of this. So what is biogas? It's just a mixture of methane and carbon dioxide. And what is a composition? So it's 55 to 65% methane, and CO2 is about 30 to 40%, with trace amounts of hydrogen and hydrogen sulfide. So it's not so much. And this is what I was mentioning about sweetening the gas that is there in this slide, the sweetening the gas, right? Over here. So this is what is meant by sweetening the gas. You remove the H2S because H2S is it's called acid gas, and it kind of it's detrimental to any downstream equipment or any engine or something that you're using it in. It's not very good for the engines, right? So you need to remove H2S, and then you can use the biogas. So the calorific value of this biogas is 20 to 23 megajoule per kg, depending on its composition. Okay. Does anyone know how to calculate the calorific value using just the composition? So let's say that um, the biogas contains 60% methane and 40% carbon dioxide. Okay. So this is in volume basis, or you can take it as on mole basis. Okay. So what happens is 60% and 40%, and the calorific value of methane is 50 megajoule per kg. What is the calorific value of carbon dioxide? Anyone? Okay, what is calorific value in the first place? Can someone answer that question? That's a very basic question.
The amount of energy released per unit per kg of fuel burned.
Yeah, per kg or per cubic meter or whatever, or per mole. It could be anything.
Okay. Okay, sir.
Okay. Anyway, moving on. Let's okay, so we were talking about how to calculate the calorific value of the mixture using the composition. Tell me the first step, and then I'll tell you the rest. At least the first step. Okay, the first question is, what is the calorific value of carbon dioxide? Answer that question, and then I'll tell you the rest. Just answer that much.
Sir, I think it's zero because carbon dioxide is the byproduct when something is burnt. There is no
It's
further.
not. It's not like a byproduct. It's not a fuel. Carbon dioxide cannot be burnt. Can you burn
Yes,
carbon
sir.
dioxide?
No, sir.
Yeah. So
No.
it's zero, right? Now you have methane, which is methane is a fuel, right? You can burn methane, right? So you have methane, you have carbon dioxide, you have 60% methane and 40% carbon dioxide. Okay. So 60% methane is so this is on molar basis or volume basis. Now what you do is you take the molar LHV of each of these gases basically. So what is what is the molecular or molar mass of methane? Can you answer that?
16.
16.
Yes, 16 kilogram per kilomole, right? So that is the molar mass of methane. Now I've told you that the LHV or the calorific value of methane is 50 megajoule per kg. Now what you need to do is convert this into kilojoule per kilomole. How would you do that?
Sir, could you repeat it? I was not.
Okay. Okay. See, so you have methane. So I told you the calorific value of methane is 50 megajoule per kg. Okay. You know the molar mass of methane, right? What is it? You just answered. Some
16.
people just answered 16. Okay. Now I want you to convert this calorific value on a molar basis. So you have it on mass basis, that is kilo or megajoule per kg. You convert it into kilojoule per kilomole, or yeah. You tell me how you would do it, and I'll tell you a very good trick you can follow in such kind of questions that will even help you in your exams and even further. Okay, first you tell me this, and then I'll tell you the trick.
It's in megajoules, right? So
Yes.
you would have to multiply it by 10 to the power 3 to get kilojoules.
Yeah. So how much is that in kilojoule?
In like the I am
So,
not
so
very
what is the
sure.
unit? What is the unit I mentioned?
Megajoule per kg.
Yes.
Was it?
Now
Yeah.
you are multiplying it by 10 to the power 3. What will you get? The units?
Kilojoules.
Kilojoules? You will get just kilojoules.
No, we need to convert the mass into molar mass, right?
No, no.
Sorry, moles, moles.
If you multiply it just by 10 to the power 3, what unit will you get?
The megajoule is gonna get converted to
I need to know the complete unit.
uh kilojoules per kilo uh mole. Is it?
How is it kilomole? What was it before?
Sir, wait. We need to. I okay. I'm so confused right now.
Okay,
What are
you
we?
don't have to be okay. I'll tell you the trick right now. Okay, take the units. Always you look at the units. Okay, that's very important, and that will give you the complete picture, or you can very logically attack the problem. Okay.
Okay.
So I told you that it is. So I told you the calorific value in megajoule per kg.
Okay.
So if you have a pen and paper, please write it down so that you won't get confused. Right, megajoule per kg.
Yeah.
Now you are telling me you have to convert. I asked you in kilojoule per kilomole. So you have to convert the megajoule per kg into kilojoule per kilomole. So how many conversions are there in total in this?
Just two.
Yeah. What are the two? What are those two?
From megajoule to kilojoule and from mole to kilo mole.
Huh? Sorry.
Right.
From
Uh,
kg to kilomole.
yeah,
Yes.
kilomole. Sorry.
Kg
Yeah,
to
kg
kilomole.
to kilomole.
So you have to do two conversions. So what
Yeah.
is the first conversion?
10 to the power 3 to
Yes.
convert the.
So I told you. So if you do that, what will be the intermediate unit that you will get?
Kilo.
Gigajoules.
Huh?
No,
Wouldn't it be
Kilojoule
gigajoules? Sir?
kilojoule per
kg.
kg.
Yes,
Yeah.
Kg.
exactly. Kilojoule per kg.
Yeah.
Because you
Yeah.
are not
Yes.
focusing on the kg yet.
Yeah.
Okay.
Yeah.
Yes.
So from megajoule, you've gone to kilojoule. How much is that? What the value? So I told you 50 megajoule per kg. How
Yeah.
much is that value in kilojoule per kg?
50,000.
Yes, 50,000
50,000 kilojoule
kilojoule
per
per
kg.
kg.
Yeah.
That is your
Yes.
intermediate unit. Now you have to target the kg part. Now you have to convert that into kilomole. How will you do that? Look at the units again. Okay. So you have this kilojoule per kg and you have the molar mass of methane. So
Yeah,
what unit
it's
is that in?
molar mass by mass.
No, you do it in units only, because if you try to remember the formula, it's going to be a mess. Okay. You can if you have a good memory power or something. But that's not recommended. Do it in units. So you have kilojoule per kg. What units? What is the unit of this? Uh, molar mass.
Uh, what?
Grams.
Yeah. Uh, no, in this it's
Yeah,
kg.
it could be anything,
Mole.
but I mean, no. What is the molar mass? I mean, the unit of molar mass. What does molar mass mean?
It's the total mass of all the atoms.
Yeah.
In this
It's
case,
the
it's
it's the mass of 1 mole of any substance. That is molar mass, right?
yeah.
So what is the unit here?
It's just grams or kg
Grams.
or
Yeah,
AG,
grams.
of course,
Is it just grams? It's not just grams. No, you need to. I mean, grams of what? Grams per what?
per mole.
Yes, grams per mole. Or if you
Yeah,
want, because I've asked you in kilomole, it is kilogram per kilomole, right?
yeah.
Okay. So now you have what are the units you have here? So what is the calorific value at the intermediate unit? And you see the molar mass units.
So you have to multiply the intermediate value with the 16.
Yes, but why is it? Explain that.
Because the 16 is kilo. What is that?
Do it in terms of units only. So
Yes,
what
yes.
is the intermediate unit?
Kilojoule per. No, wait. Kilojoule
Kilojoule
per
per kg.
kilomole.
No, the
Kilojoule per kilomole.
what is the intermediate
Kilojoule
unit?
per kg.
Kilojoule per kg. Okay.
Yes.
And what is the molar mass unit?
Kg per
kg per
mole.
mole.
Kg
Yes,
per
kg per
kilomole.
mole. Kg per
It's
kilomole. Yeah.
kg per
So
mole is
in order
also
to cancel
okay,
out,
but let's follow one convention. So since you said gram per mole, it becomes kg per kilomole. Okay.
kilomole. Yes.
So now you
In
have
order to
these two
cancel out the
units.
kg,
Yeah, exactly.
in order to cancel out the kg, we'll have to multiply it here.
Yes.
50 into 10 to the
Yes.
power 3 into 16.
Yes. So what happens here is you have kilojoule per kg and then you have kg per kilomole. If you multiply both kg on the numerator and kg on the denominator, they get cancelled out.
Cancel
What
out.
is remaining?
Divide the denominator, we have a kilomole.
Yeah, and the numerator?
Kilojoules.
Yeah. So I mean, tell me the entire unit. Like.
So the answer is
Kilojoules per kilomole.
Yeah,
yes,
kilojoule per kilomole.
Yes, sir.
So now, I mean, through the units, you are figuring out the formula. That's how it is.
Yes.
If you try to remember the formula and then try to fit it in, it will not work, because sometimes you may get confused. Sometimes you may get confused as to do you have to divide or multiply or what is it. So you target the formula, you target the units. Okay, you see what the units are, which gets cancelled. So you know what you need at the end, what your answer should be, and you know what you are given, what are the units of all the parameters given, what kind of operations you need to do to arrive at those units. Always look at that. So in that case, what happens? You can just write it down on a piece of paper and say that, okay, in terms of units, this is what it is. I have to multiply kilojoule per kg times kg per kilomole to arrive at kilojoule per kilomole. But I'm given megajoule per kg. So the first conversion is megajoule to kilojoule. So I multiply 1000. Okay. And then you figure from that you have already figured out the formula. So you can just substitute all your numbers and you can get the final answer. Did you all get this? Because this is very important. I mean, it will help you in the exams. It will help you everywhere else, literally. Okay.
Yes, sir.
So if you guys didn't get this, please ask me. If anyone didn't get how this is done, please ask me.
So the part where you multiply
Yeah.
kilograms per kilomole, like I didn't get that.
Okay. Have you written this down?
Yes, sir.
So look at the units. So what units do you have for the intermediate unit that you got for the LHV or the calorific value?
Kilojoules per kg.
Okay. And what is the unit of molar mass?
Kilograms per kilomole.
Okay. Now you have these two. Okay. Now I told you I need the molar calorific value. That is calorific value on a per mole basis or per kilomole basis.
Okay.
Which means your final unit should be in the terms of in terms of kilojoule per kilomole. Got
Okay.
it?
Yes, sir. Yes.
So what you have these two units, you have to have a final this third unit which you need to get from these two units. What operation should you do between these two units to arrive at that third unit?
You have to multiply both.
Yes. What happens if you multiply?
Then you will get the molar calorific value.
No. I mean, tell me what happens. I mean, what operation have you done there to arrive at that third
Okay.
unit?
So kilojoules per kg into kg per kilomole. So kg and kg gets cancelled. You get
Yes.
kilojoules per kilomole.
Yeah. So you are left with kilojoule per kilomole, right? So
Yeah.
which means that if you want the molar calorific value from the mass calorific value on mass basis, you have to multiply it by the molar mass. That's it.
Okay. Thank you.
Okay, that is the formula. But if I tell you that, you will say, okay, you will write it down today and you will forget it tomorrow. This way you will forget remembering it. You can you can just write down these units on a piece of paper even during the exam, and then you can figure out the formula and everything yourself. Okay. So remember this trick. It will work not only in thermodynamics. It will work everywhere else wherever there are units involved. Okay. Okay. So can you tell me the value of kilojoule per kilomole, like the value of the calorific value?
800 into 10 to the power 3 kilojoule per kilomole.
Yeah, which is 800,000 or 8 lakhs. Okay.
Yes.
So let
Yes.
that be there now. So now I told you that you have 60% methane and 40% carbon dioxide on molar basis. So volume and mole you can interchange when it comes to composition. That is basic science that you would have read in 12th standard. You know that 22.4 or 22.6 liters per mole, something like that, right? 1 mole contains so many liters, something like that, right? Okay, let's not go into that. Okay. So consider 60% of methane and 40% of carbon dioxide on a molar basis. Now, can you calculate the molar calorific value of biogas using this? Using this composition, basically. What should you do? I mean, let's go step by step. What should you do to obtain this? Logically speaking, what must you do? Like, okay, let me phrase it this way. Okay. Now let's take 1 kilomole of biogas. 1 kilomole of biogas. it has 60% methane, which is 0.6 kilomole of biogas it has, and 40%, that is 0.4 kilomole of carbon dioxide. Okay. Now you know what is the molar calorific value of methane. Okay, which is 800,000 kilojoule per kilomole. That is for 1 kilomole, it contains 800,000 kilojoules. How many kilomoles do you have in biogas? How many kilomoles of methane do you have in biogas?
0.6 kilomole.
0.6, sir.
Yes. What is the calorific value of carbon dioxide?
0, sir.
0.
0.
0. Okay. How many kilomoles? Which is what is the unit? Can you tell me the unit of? I mean the carbon dioxide calorific value.
Kilojoules per kilomole?
Yes, it could be any unit. I mean, it's 0. So you multiply 0
Yes,
by
it's 0.
anything, it's going to be 0 only, right?
Yes.
So it is 0 kilojoule per kilomole.
Yes.
So 1 kilomole of carbon dioxide contains 0 kilojoules. 1 kilomole of methane contains 800,000 kilojoules. How many kilomoles of methane is there in biogas?
0.6.
0.6.
0.6.
How many?
Yes.
Yeah. How many kilomoles of carbon dioxide are there in biogas?
0.4.
Yes. So you have 0.6 and 0.4. Now you know what is the value for 1 kilomole. Can you calculate for 0.6 kilomole? Can you calculate for 0.4 kilomole?
For 0.6 kilomole, it is 480,000 kilojoule per kilomole.
Yes. Not kilomole, because this is for 0.6. It's only the kilomole part will come later.
Okay.
You get it? Because you're taking 1 kilomole of biogas here.
Yes, yes.
Okay. You're taking 1 kilomole of biogas here, out of which 0.6 kilomole is methane and 0.4 kilomole is carbon
0.4
dioxide.
is carbon dioxide.
Okay. So because you have for 1 kilomole, you have 1 kilomole of methane contains 800,000 kilojoules. Now, since you have only 0.6 here, you multiply that by 0.6 and you get 480,000 kilojoules are available in that 0.6. Now, the
Yes.
next one is carbon dioxide. How many kilojoules are there in carbon dioxide? I mean, 0.4 kilomoles. 0.
Yes.
You have to add both.
Okay.
So this is called weighted average. You would have heard this term, weighted average. So based on the composition, you just multiply the composition with the respective molar calorific value. And if you do that and add it, you'll find the calorific value on kilojoule per kilomole basis of the entire biogas. Do you get it?
Yes.
Anyone who has some doubts on this? Anyone?
Sir, you said weighted average for the whole gas. That would be calorific value of methane
So
and CO2.
no, weighted average is a mathematical concept. I think you would have come across this weighted average, right?
No, sir, I have
So,
not.
okay, let me give you an example. What example can I give? Okay, example can I give? Okay, let's take income for example. Okay, let's say there are two people, you and me. Okay, I earn, let's say, 1 lakh per month, and you earn 2 lakhs per month. Okay, right? And so what is the average income here? between the two of us?
1.5.
1.5.
Okay, 1.5 lakhs. Okay, because there are two people and there is no weightage to either one of us. Okay. So that means that okay, how do I put this across? I'm not exactly sure. Okay, let's say there is a corpus fund of let's say 3 lakhs. Out of this, out of which I'm given 1 lakh and you're given 2 lakhs. So what percentage of the corpus I'm getting and what percentage are you getting?
0.33 and 0.66.
Yeah, so I'm getting 0.33 and you're getting 0.66. Okay. Now, if you have to follow the same method everywhere, the same proportion everywhere, let's say there is a corpus of 10 lakhs. How much will I get and how much will you get?
3.3
3
lakhs and
lakhs,
6.6
yes,
lakhs.
6.6. Yeah.
Right. So that is basically the concept of weighted average. Okay. So if you have some factor that is actually affecting, so instead of just saying, okay, I earn 1 lakh, you earn 2 lakhs, so the average is 1.5, you just divide it by 2 or divide it by n. N is the number of samples, right? So instead of doing that, if I say that, okay, there's a corpus of 3 lakhs, I get 1 lakh and you get 2 lakhs. So that changes everything because now I'm getting 33%, you're getting 66%. If the same trend continues, then if the corpus becomes 10 lakhs, I'll get 3 lakhs, 3.3, you'll get 6.6 lakhs. Okay. Do you get the point?
Yes, sir.
Okay. So it's very similar to that here. Okay. It's the same, in fact, because there is 60% of the there are 60% is occupied by methane and 40% by. Okay, can you mute yourself? Just mute. Yeah. So 60% is occupied by methane and 40% by carbon dioxide. So if you say that if you want to take a simple average, what will you say? Okay, it is 800,000 and 0. So the average calorific value for biogas is 800,000 plus 0 divided by 2. So that is 400,000. But that is wrong, right? Because 60% of the share goes to methane. So you have to allot 60% to methane and only 40% to carbon dioxide. You get the point?
Yes, sir.
Yes, sir. Yes, sir.
Okay, so that is what I meant by weighted average. Okay. So that's how. So what is the total calorific value of biogas here?
480,000 kilojoule per mole.
Yeah, kilojoule
Yes,
per
sir.
kilomole. Okay.
Yes.
So that is the calorific value of biogas.
Methane.
Now
Biogas.
you have to convert that back into what do you call on mass basis. How do you do that?
Megajoule per kilo. Megajoule per kilogram.
Yeah, megajoule per kg, or let's do kilojoule per kg. So what do you need here to convert it back into mass basis?
We need the molar mass of both methane and carbon dioxide.
You need the molar mass of biogas.
Biogas, yes.
How do you calculate that? It's the same way, like you said, molar mass of methane and molar mass of carbon dioxide. Okay, you
Yes.
calculate the total molar mass using that 50, 60 per, again, it will be the same.
Yes, weighted average.
Because it is in kg per kilomole, right? So you have
Yes.
methane in kg per kilomole, which is 16, and carbon dioxide is 44 kg per kilomole. Okay. But you don't have 1 kilomole here. You have 0.6 kilomole and 0.4 respectively. So you do the same thing. 0.6 multiplied by 16 plus 0.4 multiplied by 44 will be the total, will be the molar mass of biogas. Got it? Can you just quickly calculate that? Did you all get this point? What I'm trying to make here?
Yes, sir. So the total molar mass of biogas is 27.2 kilogram per kilomole.
Yes. Did
That is
everyone else get this? I mean, this is important. Not only for this lecture, this series, it's important even for your, for your studies and further. Did everyone get how to calculate the molar mass of a mixture of gases? So this is basically the mass and energy balance that I was talking about, that I'm supposed to take after a few classes, but it's okay. I'm giving you an introduction right now. Okay. Guys, please speak up. If you have any doubts, please ask. Okay. Because your activities will be very much related to all of these things. Okay. Whoever is signed up for the activity, it'll be completely related. I mean, this is just maybe 1 or 2% of the activity. You have to use this, calculate something else, do something else. Lots of things. Okay.
Yes, sir. So what we basically do is
Mm-hmm.
the percentage of methane into its molar mass plus the percentage of carbon dioxide into its molar mass. Am I correct?
Yeah, exactly.
Okay.
So if you look at it from the perspective of units, you have the molar mass of each of these components in kilogram per kilomole. Okay. That is, for 1 kilomole of methane contains 16 kilograms. Okay. So that is the idea of molar mass, right? But here there is only 0.6 kilomoles. So how much is it? So multiply by 0.6, you'll get how much of methane is actually there in biogas. Similarly for carbon dioxide, add them both, you will get the total molar mass of biogas itself. So here you have 0.6 times 16, which is the molar mass of methane, and zero point 0.4 times 44, which is the molar mass of carbon dioxide. And you get 27.2, which is a molar mass of biogas. Now, can you tell me what is the calorific value of biogas on mass basis?
So 17.65 kilojoule per kg.
Are you sure?
Yes, sir. No,
Are the
into 10 to
units
the power
correct?
3. 10 to the power 3. Yes, sorry.
Yeah.
Yes. 16.65 and 17.65 into 10 to the power 3 kilojoule per kg.
So if you want to express that in megajoule per kg, how much is that?
Yeah. 17.65 megajoule per kg.
That's it. So that's your calorific value of your biogas.
Yes.
So did you get this? Did everyone get this point? Like how the calorific value is calculated? The whole thing,
Yes, sir.
right? Okay. So here it is mentioned 20 to 23, but that depends. Like if you go to 65%, 70%, and so on, okay, then obviously the calorific value will increase. Okay. So based on what I gave you, 60 and 40, it's going to be 17.65 megajoule per kg. Okay. We have not moved for past 4 slides, but okay, let's do one thing. I'll just do half of this today and then we'll push the rest to tomorrow. That I can do. Okay. So what are the phases of biomethanation? So we spoke about this briefly. There are 3 phases. So first is hydrolysis, where the insoluble biodegradable materials like the cellulose, polysaccharides, they are all broken down into soluble carbohydrates and fatty acids. This is also a biological process. There are some organisms that secrete some enzymes. Okay, they create some enzymes, and that those enzymes help in breaking down all the complex material, complex polymers into simple carbohydrates and fatty acids. So these soluble carbohydrates and fatty acids are further converted into organic acids by acid-forming bacteria. Okay. So organic acids are formed in the second phase. In the third phase, the acids are converted into methane and carbon dioxide. Very simple. So you have three phases. One is hydrolysis, then comes the acid formation, and third is methanogenesis. So the ideal pH range for the optimum performance is 6.5 to 7.5. It should be very close to water pH. Okay, and the temperature range could be between 20 and 55 degrees Celsius, but normally we are going for mesophilic because this has the highest efficiency, and I mean, the conversion is very good. The conversion rate is very good for mesophilic ranges, like between 25 to 35 degrees Celsius. Above that, the conversion rate drops, and even below 20, the conversion rate drops. Okay. So the general equation is okay, CHO complex, right? So this is biomass. Okay, and it produces so much of CO2 and so much of, okay, this is not properly mentioned here. Okay, I'll let you know the equation. There seems to be some formatting error here. Anyway. So this is a flow chart of this. So like I said, the phase 2 can be broken down into two phases. One is acidogenesis, where some acids are formed. Acetogenesis, where acetates are formed. So acetogens, which produce from all the propionate and butyrate, etc., it produces two types of products. One is a combination of hydrogen and carbon dioxide, and then some acetates are formed. Then you have the third phase, or in this case, fourth phase, which is methanogenesis, which contain methanogenic bacteria, okay, which reduces carbon dioxide into methane, and acetates, again, they convert into methane. Okay. So what are the factors affecting the production of biogas? So one is pH, we already spoke about. Okay. So what happens in this case is because of the second stage. So in the second stage, because acids are formed, the pH of the entire reactor drops. Okay. But then once the methanogens come, they break down the acids to form methane. It rises again. So it kind of it has a delicate balance, the pH. So in the second phase, the acids are formed and the pH is like decreasing. And then in the third phase, once the methanogens take over, the pH again increases. Okay. But of course, the ideal pH is so to maintain this ideal pH, we have to do some dilution. Okay, we cannot just we cannot just have solids just like that. It has to be diluted in water. Okay, so the total solid content should be between 8 to 10%. And the loading rate, so there are volatile solids present within the biomass, right? So that should be between 0.5 to 1.6 kilogram per meter cube of the reactor per day. Okay. So seeding is very important. So what is seeding? So there are two types of bacteria. One is the acid forming bacteria, and the second is methane forming bacteria, methanogenic bacteria. So the acid forming bacteria, they reproduce quite quickly and then they increase in number. But the methane forming bacteria are slow to respond. Okay. So in that case, what happens? There is an imbalance. There'll be a lot of acid and very less methanogenic bacteria to act upon it. So then the reaction comes to a stop, or it moves very slowly because of this issue. So here, how do you solve this issue? You can just have a culture of methane forming bacteria. You can add it along with the biomass, so that the population of both types of bacteria are maintained. Or you could also have two stages of reactors where the first phase or first stage is like the acidogen. So the acid forming bacteria forms the acid. Okay. And then in the second stage, that acid, the weak acid is taken, and then the methanogenic bacteria is there, and then that forms the methane and carbon dioxide. So both phases are like completely separate. It's in separate containers. That can be done. Uniform feeding is very important. Like if you have to feed the same amount. So if it is a continuous reactor, you have to feed the same amount of organic material every day at the same time of the same quality. Only then you can maintain the biogas output. The carbon to nitrogen ratio should be maintained. And why is that? Because both are very important for the bacteria. So carbon is required, or the carbon in the organic matter is required for energy purposes. Okay, so the bacteria uses the carbon to run its day-to-day lives basically. And the nitrogen is what through proteins they'll get, right? So nitrogen is important for building their cells and tissues, and right, so that it's very important for that. But the carbon is consumed 30 times more than nitrogen. That is because of the complete activity, right? And it is the bacteria is very active. It needs more energy than building the body basically. So the carbon is consumed 30 times quicker than the nitrogen. So you maintain that ratio in 30 to 1 ratio. So if you have 30 parts of carbon in the organic matter, you introduce nitrogen in some way. If you find that the nitrogen is not enough, or maybe it's too much depending on the biomass used, so you have to make sure that it is maintained at this ratio. The diameter to depth ratio, that is also important. Although there is no consensus on what ratio this is, optimal production of biogas. Some say it is between 0.66 to 1. That is the ratio that normally people say. Okay. So nutrients, I already talked about carbon and nitrogen. So you also have hydrogen, phosphorus, and potassium. Okay, that is also important. The retention time and rate of feeding. So retention time should be between 30 to 45 days, and sometimes it can even go up to 60 days. Okay, so the organic matter should remain in the biodigester for 30 to 60 days. Okay, so like we spoke about this, the type of feedstock, it can be plant or animal matter with low lignin content. Okay, and to reduce the toxicity in the biodigester, so the digested slurry must be removed time and again, because the digested slurry contains a lot of inorganic matter, and that is very toxic to the bacteria. So if that digested slurry keeps increasing, then the reaction will stop. Okay, because there is no more bacteria. Either the bacteria becomes low, or the bacteria will just die altogether, because there literally is nothing of substance that the bacteria can use in that biodigester. Okay, so the digestion is better at lower temperatures. And yeah, we spoke about this. So if the acid forming bacteria population increases, then there is acid accumulation in the digester during this phase. So that we can use a two-stage reactor or something, where the acid is taken out, and then the methane forming bacteria can break it down into biogas. Okay. So, okay, I'll just quickly go through this, and then we'll stop for today, because it's already 8, and then we have to also discuss about the final assessment, right? So the biogas plants can be classified on different bases. So based on output rate, it can be continuous type or batch type. So what is continuous type? So raw materials are fed continuously, and then even the biogas is produced continuously. So there is no kind of break in between. Okay, the break is taken only for the cleaning of the tank and maintenance, basically. That's it. Okay. In the batch type, what happens? So you have one I mean, you just have an input, and that stays there for however many number of days. Like, let's take the retention time, 60 days. So you have this for 60 days. After 60 days, you remove all the gas, you remove the slurry, and then you clean the tank, and then you put it again. So it's that way. It's not like happening every day. You're not getting a continuous supply. So based on design, there are two types of designs. One is the floating drum type, and the second is a fixed dome type. So a floating drum type. So there are two parts in the digester. One is the digester itself, where the reaction is happening, and then on top of that, you have the gas holder, because the gas comes to the top, right? And you have to hold it somewhere. You have to store it somewhere. So the digester is always fixed, okay, in both types. But then in the floating type digester, you have the gas holder that is floating type, that is on top of this digester. You have an inverted kind of drum, okay, which is made of mild steel or metal basically. And then it is on the sides, it is locked by a water seal. Okay, so that the methane, or the biogas cannot escape from the sides. Okay, so when the gas is produced, as the gas is produced, this because it's floating, the drum rises to the top to adjust for the pressure. But in the second type, the fixed dome type, what happens is the pressure increases, keeps on increasing, because as more and more gas is formed, there is a lot of pressure on the walls, right? But you can't really release the pressure there. You just have to build it for high pressure. Okay. So in the floating time, I told you about the water seals, and the floating drum is made out of it's made out of mild steel or ferro cement construction. And recently, there has been polyethylene and fiberglass reinforced plastics. These have come recently. So these are the basic differences, the basic classifications. So from slide 10, we will look at this tomorrow, right? Until here, do you have any doubts?
Sir, so I have seen floating drum type at a friend's place.
Right.
So this is the floating drum type is usually for small scale, right? Like it can't be made for a large scale.
Yeah, normally, yes. Normally, yes.
Right?
Because see, the thing is, the drum should be on top, as in above the ground. Okay, in the
Yes.
fixed dome type, you can do it even underground.
Okay.
Okay, so yeah, that is one thing. But yeah, in general, the floating drum type is like small scale. You're right.
Yes.
Any other questions, even on the calorific value and um, molar mass, all of these things? You can ask any doubts if you have. Okay, no questions? Okay, so the Q&A we'll do after everything is complete. Biomethanation and the fermentation.